You may have noticed in the reading that you did for your assignment that you were really reading about a lot of the things that we covered in our last lesson. And some of the things that you read about the day before that are things that we're going to cover in this lesson. Well, I wanted to be able to look at the pictures and to be able to understand by using those pictures, so I really felt like there was a certain order that I needed to go in. By the end of today, we will have finished section 7A, and so I think you'll have a good understanding of that. So I apologize for things being a little bit out of order, but that's the way it just seemed like it fit best. I would like for us to go back and look at the photo from the last lesson, our last photo there, because there's something else that I want to show you with this. Hey, remember this? We have our astronaut there. Now I've got a line drawn there. That line actually shows where the moon's surface is. I want you to notice where the astronaut's feet are. Up in the air, okay? He has jumped quite high. That spacesuit is very heavy. So let's ask ourselves a question. What does his being about 1 meter up in the air tell you about the moon? Well, I want you to think gravity. We've talked about gravity several times. We discussed the strength of the sun's gravity and of Jupiter's gravity, both of which are strong enough to tear comets apart. You couldn't begin to jump if you were on Jupiter or if you were on the sun, but on the moon, even dressed in a heavy spacesuit, astronauts can jump quite high. And that's because the moon's gravity is only 1/6 of what it is on the Earth. So to find your weight on the moon, multiply what you weigh now by 1/6. Now, everything that's affected by gravity on Earth is going to happen differently on the moon. I'm going to tell you, some people say, try to say anyhow, that astronauts never ever landed on the moon, that that's just all a hoax. Well, we're going to talk about that more, the moon landing, that is, more in the next chapter, but let me assure you that the way that astronauts walked because of the low gravity is not something that they would have been able to fake. I mean, watch these guys walk around. This is not something that you could even do on Earth, especially if you were wearing this heavy space suit. And this is actual footage of astronauts on the moon. There you see one playing golf. But notice how strange it was the way he walked. Why does he walk that way? Because the gravity is just 1/6 of what it is on the Earth. I want us to think back to the moon's thin atmosphere. Why is it thin? Think about what you've just been told about gravity. The atmosphere is thin because the moon doesn't have enough mass to hold on to an atmosphere. You see, the mass of an object determines its escape velocity. Now, you've heard this term before. Let me just remind you, the escape velocity is the minimum speed an object must have to free itself from gravitational pull. Escape velocity is also affected by the mass of whatever is trying to escape. So in the case of an atmosphere, we're talking about the air, okay, which doesn't have very much mass at all. In fact, let me make a comparison for you. Escape velocity of the Earth, 11.2 kilometers per second. Escape velocity of the moon, 2.4 kilometers per second. In other words, it doesn't take nearly as much effort for the air to depart from the moon as it does for it to depart from the Earth. The Earth is able to hold on to it. The moon is not able to hold its atmosphere. Now, do you see how the moon's thin atmosphere and its weak gravitational pull are related? While we're talking about escape velocity, I want you to think back to chapter 3. Now, I realize that was a long time ago, but do you remember talking about black holes? What do you think their escape velocity is like? I want you to consider this. They don't allow light to escape. And in a vacuum, light travels at 300 million meters per second. That means it takes an extremely dense object to have that high of an escape velocity. Escape velocity is dependent on mass. And I know it's sometimes hard to keep the difference between mass and weight straight in your mind. So I'd like for us to take a look at facets of astronomy. Weight versus mass. This is on page 146.
So what great product do you have for us today, Bill?
I'm glad you asked, Johnny. I'm here to tell you about my patented weight loss program. It's guaranteed to reduce your weight to a fraction of what it now is in only the time it takes to blast off into space.
Well, sounds great, Bill. But how is this possible? You have unhealthy diets or rigorous workout routines?
You would think so, but no. My special program requires no sacrifice of enjoyable food or personal pain. We simply put you on a short trip to outer space where you lose almost all of your weight.
Wow, that's incredible, Bill. Why don't you tell us how you do it?
Well, a common misconception is that kilograms measure weight, but they don't. Kilograms measure mass. Mass represents the amount of matter in an object and can't be changed just by moving the object. Let me give an example. A satellite has the same amount of matter on Earth as it does when it's orbiting in space. Its mass is the same, but it weighs a different amount. You can calculate your mass by dividing your weight in pounds by 2.2 to get your mass in kilograms.
Well, wonderful. But how does that help your weight loss program?
Glad you asked, Johnny. Weight measures how hard gravity pulls on an object. The units that measure weight are called newtons. To find how many newtons you weigh on Earth, follow this formula. Multiply your mass in kilograms by 9.8. That's the rate of gravitational acceleration on Earth. On Earth, an object's speed will increase 9.8 meters per second until it reaches its terminal velocity. Around a weaker gravitational force, you multiply your mass by a much smaller number. For instance, on the moon you would multiply your mass by 1.6 to find out how much you weigh. So, the weaker the gravitational pull, the less you weigh.
But does your weight loss program actually make people thinner?
Well, no. But it makes people lose weight, and that's what counts, right?
Actually, I think that even though most people talk about weight, what they really want is to be thinner. They want less mass.
Well, on to my next scheme then. Golfing in space. Now that's guaranteed to help lengthen your shots.
Well, I trust that helps you to understand just a little bit better the differences between those terms. I do want us to go back to that same photo one more time. You're probably saying, what else can I learn from this? Well, I want to ask you, what does the scenery look like? I mean, do you see any trees? Do you see any grass? Do you see any signs of life? Well, besides the astronaut that's there. No, you don't, and that's because there isn't life on the moon. There are a bunch of rocks, though, and astronauts have spent all kinds of time studying those rocks. This involves the science of geology, and we're going to spend quite a bit of time studying rocks on the Earth. But for now, we want to consider rocks on the moon. The geological study involves more than just finding the rocks and breaking them with hammers. In this photo, you see a very large boulder at the Apollo 17 landing site. Do you have any clue where it came from? The moon. Well, yes, I realize that. But, if you could back up and get a bigger picture of this, you could see that this boulder probably rolled down the hill that is nearby. And, of course, that's something that the astronauts were looking around. There's a big rock here. Where did it come from? Has it always been here? And they were able to see, no, it came from a higher area. Gravity did bring it down. Now, big rocks aren't the only ones that are studied to find out more about the moon. Astronauts also study the little ones. Here you see astronauts raking up what are called rake samples. And these are like, walnut-sized rocks, but they do give a good sampling of the types of rocks that are found on the moon. Now, you'll notice, though, that the moon's surface isn't super rocky. It's mostly just powdery, so they, won't always find rocks. Now, this is a photo of a rock from the moon, and it's called an anorthosite. It's a very common type of rock found on the moon. I want you to take a good look at that because I'm going to show you another moon rock. I want you to compare them in your mind, all right? So that's one type of moon rock. Here is another one. Notice it does look different from that last one I showed you. This one is called a breccia, which means that it's rocks and minerals that are kind of mixed together, kind of like a conglomerate of rocks. And this rock was collected by the Apollo 16 mission. Now, is everything on the moon the same? No, it's not. You have been able to see that the terrain is totally different. Even the rocks are different. Now, I don't know about you, but I'm not used to thinking that hard about photographs. But I think you have to agree with me that we've learned a lot from them. As As we think about our moon, we know that the moon is something we can see, just about every night. Perhaps, if the weather is not conducive, it might be a night or two that we can't see it. Also, when there's a new moon, we can't see the moon. But I want to ask you, how far away is our moon? Well, that's something that you can figure out on your own. Not just looking up the statistics, but you can kind of figure it out. And Miss Corey is going to show you how as you do an investigation together. So I'd like for you to, first of all, pause the program and read Investigation 7F on pages Essay 101 and Essay 102.
Although the moon is the closest celestial body to the Earth, compared with the distances we're used to on our planet, the moon is pretty far away. In this investigation, we're going to construct a way to determine the distance from the Earth to the moon. We'll use a meter stick, a clip, and a card with a hole punched in it. Now I have my viewing card already cut out, and you can see that I have cut on the solid lines and then I've folded on the dotted lines in there. Now the diameter of the hole right here is about 6.5 millimeters. And we'll use that value in our calculations later. I'll need to clip the card onto the meter stick, and when I'm outside, I'll move the card up and down the meter stick to try to fit the moon inside the hole. If you do this investigation, you may need to have someone else help move the card and clip for you if you aren't able to reach the card easily. Now I'm ready to go outside and make my observations. There's a full moon for us to look at, so let's go ahead outside. I'm going to hold the meter stick with the 0 centimeter end right below my eye. I'll close one eye and look through the hole in the card at the full moon. Very carefully, I'll move the clip and card until the moon just fits inside the hole. Now the moon is pretty bright, and that makes it hard to see its edge real clearly. I think we have a good position here. Let's take a measurement. The outer surface of the card is 75.5 centimeters away from my eye. So that would be 755 millimeters. Write that down as the distance for the hole. Use a formula to calculate the distance to the moon. Make sure you substitute the correct values for the letters. The letter R represents distances and D represents diameters. So R sub moon is the distance from the observer to the moon. D sub moon is the diameter of the moon, the actual moon. R sub hole is the distance from the observer's eye to the outer surface of the card, and D sub hole is the diameter of the hole in the card. To solve for the distance to the moon, we start with the equation distance to the moon is equal to the diameter of the moon times distance to the hole in the card divided by the diameter of the hole in the card. We substitute the values in, the millimeter units cancel out, and when we round, we find that the distance to the moon is 403,751 kilometers. Now to change over to miles, we'll use a conversion ratio that shows that 0.6214 miles is equal to 1 kilometer. When I multiply, the kilometer units cancel and I'm left with mile units. And we find that our calculated distance to the moon is 250,891 miles. At its perigee, the moon is 363,300 kilometers away from the Earth, and at its apogee, it's 405,400 kilometers. When the moon is at its apogee, it will appear just very slightly smaller than when it's at its perigee. Depending on where the moon was in its orbit, my observation could have been affected. Looking at the value we calculated, 403,751 kilometers, we could guess that the moon is probably close to its apogee. Being at apogee and perigee isn't the only thing that may affect how large the moon appears. Sometimes when the moon is close to the horizon, it appears unusually large, huge in fact. During the same night, though, it seems small when it's high in the sky. So why does that happen? What's going on there? Basically, it's an optical illusion caused by the moon being near the horizon. We don't really know exactly how it works, but we do know that the moon itself isn't getting smaller as it rises. You may think that the Earth's atmosphere could refract the light from the moon, making it appear bigger. Although the atmosphere could distort the appearance of the moon when it's on the horizon, the distortion isn't big enough for us to see with just our eyes. And the distortion would probably make the moon appear smaller, not bigger. Some people think the reason that the moon seems larger near the horizon is because there are objects there, or reference points, things like trees, mountains, city buildings, that our brains compare the moon to. Supposedly, when your brain compares the reference points to the moon, it interprets the moon as being very large. When the moon is high in the sky, your brain interprets the moon as being smaller because there are no objects up there to compare it to. Now the problem with this idea, though, is that sailors out in the middle of an ocean with no reference points on the horizon, just open water, have reported thinking that the rising moon still appeared bigger than the moon high in the sky. Another problem for this idea is that most people, if they bend over and look between their legs or stand on their heads and look at the moon, no longer think that the moon at the horizon seems large. It's strange, but it does seem to work. The moon illusion has been something that people long before the time of Christ have been wondering about. Men like Aristotle, Da Vinci, Kepler, and Descartes also pondered why the moon's size seems to change. But after centuries of men thinking, we still aren't exactly sure how it works.
Well, we can learn from photos, we can learn from observations. Another way to learn is to make comparisons. I would encourage you to try to compare new pieces of information with information that you already know. Now, you're quite familiar with the Earth, so let's make some comparisons between the Earth and the moon. Let's start by thinking about its size. We can measure this in diameter. It's a good way to do it. The distance from one side to the other is 3,476 kilometers. Now that is less than the width of the United States. So when you see a fact like that, this is the type of thing that you need to picture in your mind. How do the two of them compare? Now that picture is also in your book, so you're welcome to look at it there. And that should cement in your mind not so much that measurement of 3,476 kilometers, but the idea is, it's just a little bit less than the size of the United States. Now what about its surface area? What am I talking about when I think of surface area? It's not the same thing as diameter, is it? So I can't just superimpose one thing over top of the other. Perhaps you think about the maps of the Earth where they've taken like a globe and flattened it out, and so it has all these little, circle things up at the top. That would be showing surface area. If you want to compare that in your mind, then it's a little bit more than the surface area of Africa. Okay, so the total amount of space that you could cover with it, really similar to Africa. What about its mass? How much stuff does it have? Once again, we're going to compare this to the Earth. We'll compare it to the Earth as a whole. The mass is 1.2% the mass of the Earth. It's got a smaller mass. It also has a lower density. Now what about its shape? You see it at night. The shape is round, okay, we call that a sphere, and so we could say that the moon is basically spherical, the same as the Earth. Now there is a little difference here. The moon is almost a perfect sphere, but you know from chapter 2 that the Earth bulges slightly at the equator. This should tell you something about the speed of its rotation compared to the Earth. What does it tell you? Is it going to be faster or is it going to be slower? It's going to rotate more slowly than the Earth rotates. How do we know that, or why do we know that? Once again, think back to what you have already learned. You've learned that the rotation speed affects the size of that bulge. The faster something rotates, like Jupiter and Saturn, which rotate much more quickly than the Earth does, they have a bigger bulge, don't they? The other thing that affects that bulge is what the object is made out of. The Earth is terrestrial, the moon is terrestrial, okay? It's either, land or gas, and it's land, okay? So we know that it's not going to have as big of a bulge as a gaseous planet would. But as we are comparing it to the Earth, less bulge means it rotates more slowly. Now, if we wanted to compare our moon to all of the other moons in the solar system, we could say that it's 100 times larger than the average moon. Hey, so we've got a pretty good sized moon here, don't we? We could look at the ratio between the sizes of the moons and their planets. In other words, how does the size of the moon compare to the size of our Earth versus how does the size of one of Saturn's moons compared to the size of Saturn? And when we make that comparison, we find out that our moon is 10 times larger than any other moon with that comparison, except for Charon. Now, where have you heard that term Charon before? What is Charon? Charon is Pluto's moon. And we know that Pluto's moon is just about as big as Pluto. And I say Pluto's moon. Remember, Pluto actually has at least 3 moons that they've found right now. Charon, however, is the largest one. Now, we've seen that our moon, even though it's small, is relatively large. Why would it be so large? Well, Genesis 1:16 tells us that. It says, "And God made 2 great lights, the greater light to rule the day, and the lesser light to rule the night. He made the stars also." Ours is the only moon large enough to light the evening sky. So it's very important. Normal moon, moon of another planet, the average size moon would only light up about 20% of the sky, where our moon gives light much greater than that. All right, where else does the Bible talk to us about the moon? There's really many verses. I want us just to share a few of them together here. Psalm 104 verse 19 says, "He," of course referring to God, "appointed the moon for seasons. The sun knoweth his going down." The moon tells us about the seasons. We've talked about that already, haven't we, as we did study the seasons. So we continue to look in Joshua chapter 10 verses 12 through 13. It says, "Then spake Joshua to the Lord in the day when the Lord delivered up the Amorites before the children of Israel. Sun, stand thou still upon Gibeon, and thou moon in the valley of Ajalon." And the sun stood still, and the moon stayed until the people had avenged themselves upon their enemies. What does this passage tell us about the moon? Not only do we know that God is the creator of the moon, but we see too that God has control of the moon. And if God says, hey, stay still, that's exactly what's going to happen. Let's look at one more set of verses here. This time, once again, looking at Psalm 8, verses 3 and 4. David says, "When I consider thy heavens, the work of thy fingers, the moon and the stars which thou hast ordained. What is man that thou art mindful of him, and the son of man that thou visitest him?" I trust that this same awe that David had for God is something that you will have as well. As we study the features of the moon, it's just awesome to me to see how God came up with all these things, all these different features and so forth, and how it all works together. It didn't just happen. It was done by an almighty God. Now we have finished section 7a. Doing it, I realize, a little bit differently. In the next lesson, you are going to have a quiz over the features of the moon. So I want us in the little bit of time that we have left to take a look at the photos. Once again, this time the ones that are in your book. And let's just see if we can come up with one little thing that you can remember from each one. We'll start with the first page of the chapter where we see superimposed the moon and a map of the United States. What is this telling us? It's telling us about the diameter of the moon, the fact that it is less than the diameter of the United States. We can even learn from the cartoons that are there. Did you read the caption that says the moon's gravity is 1/6 of that of the Earth's? Walking your dog would be quite a challenge. You were able to see how the astronauts walked and how different that was. You can imagine what it would be like trying to walk your dog. Now there's a cartoon in the next page dealing with weight and mass, very similar to what you already saw. Let's look at the page after that. This shows the terminator line. Here's the terminator line on the moon, a very distinct line, very distinct difference between the light and the dark. Why? Because of the very thin atmosphere. However, as you look at the comparison, and that's what this is, it's making a comparison between the Earth the Earth here and the Moon up here, you'll notice that that distinction is not exact. It's much more gradual as it goes from the light to the dark. Why? What does that tell us? Remember, that tells us about the atmosphere, and of course that's something that we need to be thinking about. Turn the page and look at the next picture. Actually, with 3 pictures on this page, you notice they come all under the headings of craters. So that's something you should be thinking about. This crater is Crater Copernicus. You'll notice some of the rays that are surrounding it, the ejecta that has come from the impact that's there. This one gives you a very clear picture of those high, steep walls, and you'll notice the steep shadow on it as well. This is of Tycho, very close up of that, probably formed by some kind of meteor impact. Then this one to me is very interesting because we have a mare here, Mare Tranquillitatis. But notice it's not all smooth. It's not like what we think of it would be necessarily. We've got, yes, the lava flow that's filled that up, but notice what we also have. We also have craters. It has been impacted by a foreign object. We have very steep walls on these craters. We have very steep shadows that are here. So that is giving us a good indication of what the surface is really like. As we come over to the next page, that is the page talking about the mare, okay, or the maria, plural being maria, singular mare. The pictures here at the top show us mountain ranges, and you'll notice the mountains here, both here from an overhead shot and then here, shot directly from the moon. You'll notice how they rise right up. This is neat here. It looks like a river. It's not a river. That is a rill. Now what about here? Once again, a mare with a crater in it. So showing us the same idea here of, we can't say, oh, here's just a sea that's all totally flat, and then there's other areas that are cratered. No, it's not exactly that way. The sea areas can have craters as well. And then the next page I really want you to stop and think about, because this is the one that has features labeled for you. You're going to need to pay attention to this, especially as you do an application later on in this chapter. Now for your assignment, I would like for you to do an application. Application 7A, doesn't need that particular diagram. Also answer section review questions 7A-2 and be ready for that quiz I promised you over the features of the moon.